So let's look at what else is needed to enable this full stack integration. So of course that's the cryogenic qubit chip carriers that we are also providing. So here we are showing on the left side our QBoard product, which is a chip carrier targeting quantum measurements in general, which has been used to enable few qubit operations. The other one on the right is our QCage product, which is a product targeted at superconducting qubits, which we are also pushing ahead to enable some of the better performance characteristics needed as qubits needs to perform better. So what's our motivation to go into qubit chip carriers? So it's just fun to look back a few years. The Google Sycamore demonstration of a 53 qubit operator based on transmon superconducting qubits. So looking at what was needed to actually make that happen and work. First of all, a bit of flip chip packaging. You see also their microwave package with a whole plumbing arrangement of coaxial connectors going down to a PCB board with a microwave cavity, and finally that has to go on a dilution refrigerator, and all the wiring needed is just sheer impressive. So you could see also from last year publications, academic labs like MIT are also moving into perfecting this for operating their qubits both in higher numbers and with higher fidelities. Finally, also some other bigger commercial entities like Amazon Web Services in collaboration with Caltech showed also last year in Washington Post that they are also scaling this on the fridge and really moving on making some chip packaging and qubit chip carriers for their experiments. So this is all happening, and we saw a great need for servicing the broader academic market also to enable some of these platforms in the labs. So let's first look at our QBoard sample holder system, which is a modular mainboard daughter board stack. So the idea is that you have a motherboard that is mounted either in your POC loader for your dilution refrigerator or directly on the cold end of the fridge. That is then combined with an interposer and daughter board that enables you to have daughter boards that are essentially chip carriers that you can have in multiple and mount your chips onto. And then the interposer is then establishing the electrical and thermal connection to the motherboard and the rest of the fridge installation. So with our QBoard system, we've been enabling 48 DC lines with RC filtering and 16 IF lines via coaxial lines, which are then combined with the DC lines through bias tees, shown here in illustration. So you have both DC and IF inputs that then on the motherboard are filtered and combined with RC filters and bias tees. It gets transferred via the fuzz buttons in the interposer to the daughter board, and there you have a number of bond pads around the chip cavity that you can then use to interface your quantum dot devices. So what are the use cases for this? For us, our main use case is a study from our neighbors at the University of Copenhagen. So here showing a fully integrated device with 4 singlet, triplet, double quantum dots and 4 sensor dots labeled S1, 2, 3, and 4. These then connecting out to tank circuit resonators on the daughter board. So shown in the photos, these in the photo you see the 4 surface mount inductors that form the tank circuits for reading out these 4 sensor dots via IF reflectometry. So that's the measured curve. That's a reflectometry spectrum showing the 4 peak peaks dipping down for each of these resonators, and we are now enabling that you can read out each of these qubits independently via addressing the reflected signal from each of these resonances. So that's what's showcased here, doing Rabi oscillations simultaneously on all these 4 singlet triplet qubits, and reading that out again simultaneously on all 4 qubits. So for us, a real nice use case showing the few qubit operation possible with our QBoard system. So the other platform we have is our QCADE sample holder system, which is a microwave cavity-based sample holder with transmission lines for performing superconducting qubit experiments, and also entering the regime of running quantum processor units with several up to 5 or 10 qubits. So it features 24 coaxial lines and has been optimized for operating qubits all the way up to 18 gigahertz. And you can see here, we've done careful COMSOL multiphysics simulations of the cavity mode, so we see that this package has box modes that are above these 18 gigahertz. So again, a few use cases. So first of all, several labs illustrated here with measured results from New York universities, but several labs in Copenhagen and elsewhere has seen that they can get a giant increase in their Q factors of superconducting resonators. In this case, in the Shabani lab at New York University, they're seeing that compared to their own packaging system with a Q factor of under 50,000, they are moving up to over 1 million in Q factor when loading the same chip in our QCADE system. Another lab that has been benchmarking this system is the Haug lab at Princeton University. So they've been benchmarking their transmon qubits in our QCADE system, and see concretely that for a qubit device like shown here, they can get Q factors again reaching over 5 million and reproducing their world record coherence times that are above 200 microseconds. So now we're producing some of their world record results also in our packaging system.